The last part of the discussion of floating point numbers The last part of our discussion of floating point numbers is how we deal with them in the C language. C offers two levels of precision for floating point numbers, as we've already seen in the IEEE floating point representation, both a 32-bit representation for floats, as they're referred to, and a 64-bit representation for doubles. The default rounding mode is round to even to avoid that bias in rounding and always in one direction. And there's another header file that we can include that has some important constants called math.h that has constants, for example, for infinity and not a number that we can use in our programs. One thing to keep reiterating, and you need to remember, is never to use equality comparisons with floating point numbers. There's just too many slight differences that could occur in rounding or in how an expression is evaluated associatively or distributively. And we can often get unexpected results for our equality comparisons. The best thing to do with floating point numbers is to avoid equality comparisons and always do a subtraction of the two values and then attest that those two that difference is small. Okay. Another thing we should talk about is casting in C. Unlike casting between signed and unsigned integers, in this case we do change the bit representation. So for example, when we want to go from an int to a float and cast an integer value into a floating point value, we actually have to normalize that integer value, right? Get its exponent, figure out its mantissa, and then represent that in the floating point notation. So that means that integer may in fact get rounded. However, overflow is not possible. Floating point numbers can represent much larger values than we can get to with our integer representation. Okay, when we go from int to double, we can actually get an exact conversion as long as the int is less than 53 bits. Because now in the double notation, the fractional part is 52 bits long, plus that one extra bit, that one point that sits in front of the mantissa. So we get 53-bit word size, and our integers, if they're 32 bits, can fit completely in that. So there's going to be exact conversion. If we have a 64-bit integer, we might have some rounding again. And of course, if we go from float to double, we also get an exact casting, because a float is 32 bits, a double is 64, and it has a larger fraction, a larger exponent field, so it can definitely handle any number that is in the float representation. In doing conversions of doubles or floats to integers, we have a couple of issues to think about. One is that the fractional part of the floating point number may be truncated, because as we adjust it to take into account the exponent, we may shift it in such a way to lose a few bits. By convention, we're going to always round these values towards 0 as we do the conversion. Another issue is when the double or float is bigger or smaller than we can actually represent in our integer notation. In that case, we'll use the convention to set the value to t-min, the 2's complement minimum value. And we'll probably also do that for things like not a number or infinities and minus infinities. We might set to t-max and t-min, for example. Okay, so to summarize our floating point representations, here I've shown 5 different possibilities. So the 0 in floating point is the string of all zeros. And we do that for convenience because now if we ever test for 0, all we have to do is the same test we did for integers. We just look for an all 0-bit pattern, and we know it's a 0. Then we talked about normalized values where the exponent is anywhere from 1 to 2 to the k minus 2, where k is the number of bits of the exponent. And the significand is 1 point m, where m is the mantissa, what's represented in that blue portion of the number. We also mentioned that we reserve the exponent of all 1s to represent positive and negative infinity. Okay, and we're actually going to put a further condition on that it's going to be all 1s and all 0s in the fractional part. So all 1s in the exponent, all 0s in the fractional part, and of course the sign can be positive or negative. For not a number, we actually have many possibilities. The exponent is still all ones, but now the fractional part is non-zero. That gives us many, many values possible for not a number, and in fact these are used to signify different conditions under which the not a number arose. And finally, we have denormalized values where the exponent is zero, but we treat the significand a little differently, and you'll notice that in this case we'll put a zero in front of it rather than our typical 1 for normalized values. And this is used to represent to more densely represent the values near zero. Okay, we're not going to talk about denormalized values here, but they are treated in more detail in the recommended text by Bryan and O'Halloran, if you want to learn more about that. Finally, we always have to remember that all these representations suffer from the problem that there's a fixed number of bits, and that means we can get overflow or underflow. In floating point, we also have to consider the fact that even simple fractions like 0.2 do not have an exact representation. In fact, it's a repeating representation that we have to truncate at some point and round. Okay, so we can lose precision. Unlike in ints, every operation gets a slightly wrong result that is rounded from the exact result. And these can pile up, and that's why we do that round to even, to make sure it doesn't go in one direction all the time. Okay. The other thing we need to remember is that we might get different results as we apply associativity and distributivity. Those those laws do not apply in floating point numbers because of these inexact results to every operation. And lastly, yet again, I want to remind you, never test floating point values for equality. Okay, that can get you in a lot of trouble because of these rounding effects. All right, that concludes our discussion of number representations.